Hi, welcome to a lecture on beamforming with discrete constraints. By discrete constraints, I mean requiring that the pattern of the array have specified characteristics in particular directions. Now, the specified characteristics we're going to address primarily will be nulls. However, this could really apply to any constraints on the pattern, as we will see. Starting point here is the definition of array factor. And here we're talking about the array factor as a function of direction. R hat is simply a fancy way of saying theta phi. And recall that the array factor is defined as the sum, n equals 0 to n minus 1, that is n elements, I sub n times this phase factor, which depends on the element positions, p sub n, and the direction, r hat. Also recall that we previously defined maximum gain beamforming, and in particular phase-only maximum gain beamforming, as being beamforming in which we set the magnitudes of the excitations to be equal to 1, and the array factor in a specified direction, that is r hat sub naught, equal to n. In other words, equal to the maximum value that we can achieve in this expression. And then we found that the solution to this problem was that I sub n should be e to the minus, note the sign, minus j beta p sub n dot r hat naught. In other words, the phase of each term in the array factor for the specified direction should be forced to 0. That gives you maximum gain. That is, maximum directivity. So here's a different way of thinking about maximum gain beamforming. This different way will have the advantage that it can be generalized, and specifically will allow us to impose constraints. So here what we do is we start again with the array factor in the specified direction r hat naught, and we say that this should be equal to n. That is maximum gain beamforming, to be sure, no different from what we just said. But now we think about this as solving this equation for the I sub n's. Mathematically, let's think about this as solving this equation. And to get started here, we can write this out, right? We can write out each term in the series. There are n such terms, and we want these to add up to n. Now, this is a single equation representing just the one constraint, but with n unknown coefficients, namely the I sub n's. Now we rewrite this equation in matrix format. What we're going to do is take these phase factors and write them out as a row vector, and then take the currents and write them out as a column vector. Now, a row vector times a column vector gives us a scalar, and in this case the scalar is simply n. Now we're going to want to generalize this, so we don't want to continue to think of these as being a vector times a vector equals a scalar. More generally, we can interpret this as a matrix A, but in this case the matrix is just 1 by n, one row, n columns, so it turns out to be a row vector. But in general, we think of it as being a matrix. And similarly, we think of this thing as being a matrix, but in this case n by 1. And we'll call that B. And then the scalar at the end, well, that's also a matrix, just happens to be 1 by 1. We'll call that C. So the problem can now be stated as solve AB equals C for B, because B are the currents, and that's what we're looking for. Now note, this problem is under-constrained. There are many, in fact there are infinitely many solutions to this problem. We obtained only one. In fact, we avoided the problem of having infinitely many solutions by also requiring that the magnitudes equal 1, and that forced us down to a smaller number, and then we required that the phases in each term should be 0, and that resulted in just one solution. But in this more general way of thinking, we could have an infinite number of solutions, all in principle being maximum gain beamforming. So now we need another strategy to get us to one solution. And the way we're going to do that is to require that the norm squared of b be minimized. Now, first, what is the norm of b? The norm of a vector is a way of talking about the magnitude of the vector. It's a way of reducing a vector to a scalar in a way that reflects the magnitudes of the elements of that vector. So the definition is that the norm of b is the square root of the sum of the magnitudes of its elements. So you see that this is overall a description of how much current we have in the array, and essentially we're minimizing power by imposing this requirement. If we require that the norm squared of b be minimized, then what we're really saying is try to minimize power. Now, two things are going on. First, we have this equation, AB equals C, and then secondly, we're going to require minimum power. We need to have them both, because if we ask only for this, obviously the solution will be zeros, because that'll give you the minimum norm squared of b. But with this requirement, then the number of possible solutions will collapse to 1. So let's restate what we have established here. The restatement of the problem goes like this. We want argument of b, norm squared of b, which is saying minimize the norm squared of b. That's optimization. Subject to the matrix equation we just derived, which is the constraint, and will soon come to represent multiple constraints. So the problem is minimize the norm squared of b subject to the constraint, that is maximum gain in the specified direction. So this is a problem anyone familiar with linear algebra will recognize. It's a well-known constrained optimization problem, and the solution is simply that b equals this expression, where this part of the expression is sometimes referred to as a pseudo-inverse. So the idea here is that a Hermitian, A super H, a Hermitian, is defined as the conjugate transpose of A. What that means is you take each element of A, you conjugate it, and then you transpose the elements within the matrix. So sometimes this is indicated as taking the conjugate of the elements and then transposing them. Sometimes it's indicated as a conjugate transpose. Sometimes it's indicated as a Hermitian operator. These are all basically the same idea. So this approach will give us the same answer we obtained above when we required that the magnitudes be 1, which is pretty remarkable when you think about it, because it seems like we're asking different questions here and getting the same result. But it works, and I encourage you to try it both ways, just to see how that actually plays out. But first, let's generalize. Now, when I say generalize, I mean what happens if we wish to impose additional constraints, and in particular here, the most common constraint to consider is perhaps a null. So what happens if we want to punch nulls into the pattern? Well, a null can be defined as a 0 value for the array factor in a specified direction, and we'll call that specified direction r sub m, and we'll let m enumerate the nulls. So further, let's say we want capital M such nulls, so we'll go 1, 2, 3 up to m, and then we get this. We get our original equation, which was the pointing constraint. This was the thing that gave us maximum gain in the direction r hat sub naught. But now we can write m additional equations, one for each of these directions, r hat sub 1 through r hat sub m. And in each case, instead of that being equal to n, it'll be equal to 0, because we want a null, 0 value in that array factor in that direction. So now we have m plus 1 equations, and a total number of constraints equal to n sub c. So now we can rewrite this in matrix notation exactly as we did before, except now A will be a matrix. The dimensions of that matrix will be the number of rows equal to n sub c, number of constraints, and a number of columns equal to the number of elements. And the vector b remains the same, it's just the n currents. And now c becomes a vector, an nc by 1 vector, indicating the values in the directions which are being constrained. So we have a matrix times a vector gives us a vector, and the thing we're solving for is this given the known values of the matrix A and the vector C. So the solution to this constrained optimization problem is still the expression I just gave you. All that's changed is the dimensions of A. It went from being a vector to a matrix, and C, which went from being a scalar to being a vector. The solution is exactly the same. And in fact, this will work for any number of constraints, n sub c, which is less than n. So you might ask, what happens when the number of constraints becomes equal to the number of elements? In fact, you might sense that there could be some trouble in this case. Well, this case is not under-constrained, it is now critically constrained. And in this case, we have n equations and n unknowns, so the simplest linear algebra gives us the solution. It's simply the traditional inverse of A inverse times C. And there's no longer any need or effect in requiring that the norm squared of B be minimized. In other words, there's no need to require minimum power or to require the solution that gives us the minimum power. So you see, we've gone from being under-constrained to critically constrained. And we're in this situation when the number of constraints becomes equal to the number of elements. And this is what we mean when we say that an n-element array has n-1 degrees of freedom. What happens is when you have n constraints for an n-element array, there is only one solution. But if you have fewer constraints than elements, then there are always multiple solutions. So now you could ask, what happens when the number of constraints is greater than n? Well, in this case, we say the problem is over-constrained. In this case, there will normally not be a solution that satisfies all the constraints. You are not guaranteed, in fact, it's very unlikely, that you will find a solution that satisfies all the constraints. You might say, in the context of this statement, that we've run out of degrees of freedom. In this case, the best we can do is to minimize error. And by minimize error, I mean, let's see if we can find a way to make C minus AB as small as possible. If we had an exact solution to the previous problem, then C minus AB would be 0. And in fact, it is 0 if we're under-constrained or critically constrained. But when we're over-constrained, we know that we can't expect that there will be a solution that satisfies all the constraints. So what we do is we try to minimize the norm squared of that error. So the recast problem statement is simply argmin b of norm squared of the error. Now it turns out there's a simple solution for this. It's that b equals this thing, which is also referred to as a pseudo-inverse, times c. Now this may look very similar to the expression that we got in the under-constrained case, but you'll see it's subtly different. And it's the appropriate answer for this over-constrained problem. Note that there will be no guarantee that any of the constraints will be met in this case. In particular, that the array factor will be equal to n in the direction specified for the main lobe pointing, for the pointing constraint. And in fact, typically there will be some distortion or misalignment or surprises in general. Again, the error can't be 0, or is unlikely to be 0 in this case. Furthermore, the distortion and misalignment will grow worse as the number of constraints increases in general, and also will grow worse when constraints are closely spaced in angle. So for example, if you try to put a null very close to the beam pointing direction, you can expect that the errors will grow because it's hard to do that. It's hard to force a null to be very, very close to the pointing direction. So, to demonstrate all these things, let us do an experiment. And in this experiment, we'll have an n equals 4 array, 4 elements, a ULA, a simple geometry that is relatively easy to visualize, z-hat directed current moments, and these will be uniformly spaced at lambda by 2 along the y-axis. There is nothing special about lambda by 2 in terms of this analysis. It's not required. It's simply common, and it's easy to know what to expect when the elements are about half wavelength apart. We're going to limit our attention to the h-plane, that is the theta equals pi over 2 plane, because that is the only direction that we can really scan a beam for this geometry. There's no way to scan the beam in theta because there are no elements spaced in the z direction. There are elements only spaced in the y direction, so we can only scan in phi. So first, let's look at maximum gain beamforming. Just one constraint, that is the beam, pointing in the direction plus 10 degrees. By the way, if you're following along with this and doing the experiment on your own, I highly recommend you do that. Note that an expression for r hat naught will be x hat cosine theta naught plus y hat sine phi naught. So that's what r hat naught would be, and everything else just follows naturally from that vector expression. Here I'm showing magnitude of the normalized pattern function. Note that we expect that to have a maximum value of 1 because it's normalized. And I'm showing these results in linear scale, not in dB. In this case, I think it's a little bit easier to see things going on in linear scale. So here is the normalized pattern along the y-axis. Here is phi. And as expected, we get a maximum corresponding to this constraint at plus 10 degrees. So everything seems to be working as expected. Both methods give us the exact same solution. If we increase the number of constraints to 2, namely by adding a null at plus 65 degrees, that's right here, keeping everything else the same, but now solving for the currents, well, that's an under-constrained problem. You use the expressions I showed you above, and you get this result, which once again has a maximum in the expected direction and has a null in the desired direction. So that all seems to be working. We can increase the number of constraints by 1. This will still be under-constrained because we have 4 elements and only 3 constraints. Those 3 constraints are same beam pointing direction, yet again a null at plus 65 degrees, but now another null at minus 40 degrees. And sure enough, we get the beam pointing at plus 10, we get the first null at plus 65, and we get the second null at minus 40 degrees. So the theory seems to be working. Now we'll push our luck and go to n equals 4. At n equals 4, we're critically constrained. We've run out of degrees of freedom. We're no longer under constrained. There's only one possible solution. And the fourth constraint is going to be a null placed at 0 degrees. So here's the first null that we tried to place. Here's the second null that we tried to place. Here's the new null, in this case. And then the pointing direction, plus 10 degrees, is right here. So now we see an apparent shift in the beam direction. What is going on? Well, the answer is that if you look at the unnormalized array factor, the value at 10 degrees is still n, as we required. What's happened here is that the normalized pattern function goes to 1 at a different place, and that's because the array factor is achieving a value greater than n at this new location. Now this isn't wrong, it's completely consistent with the input to this problem. In other words, we still have nulls at these 3 locations, and the array factor is still equal to n at plus 10 degrees. It's just that now we've gotten a solution where the array factor can be greater than n. And so we see that as an apparent shift in the beam. Because this mathematical technique doesn't really know about beams, it only knows about the discrete constraints that you've posed. So you can extend this idea to any number of elements in any geometry. You could have a 1,000 element array with 100 constraints, and you would see similar kind of behavior. Everything would seem to work fine as expected. And then when the number of constraints starts to approach the number of elements, you would expect to see this kind of apparent weirdness, which is not wrong. It's simply no longer what you intended because this method doesn't really know about beams. So you can anticipate that there are other methods that we have to apply in order to prevent situations like this. And that's a topic for other lectures. This concludes this lecture on beamforming with discrete constraints.